With this first problem here, I'm going to try to help you a little bit more conceptually understand what we're doing and what it means as far as an antiderivative or a family of antiderivatives. If we take a look at this problem here, basically it's the same problem we just did with a different initial condition. Remember, we have an initial condition, we have a differential equation. All those things put together gives us an initial value problem, and we're trying to solve the initial value problem. Okay, but remember that the antiderivative of 2x, or the solution to the differential equation, the general solution would be x squared plus some constant. So if we did x squared plus 0, we'd have something that looked like this. If we did x squared plus 1, let's do plus 2. X squared plus 2, we'd have a graph that looked like that. If we did x squared plus 4, let's say, we'd have a graph that looked like that. And if we did x squared plus, or let's say minus 3, we'd have a graph that looked like this. Believe it or not, it's hard to believe this, but x squared minus 6 is down here. These graphs will never intersect. So no two graphs will go through the same points on our coordinate plane. Okay, so the idea here is that we see all these different antiderivatives. These are all solutions to our initial value problem. So it could be one of any of these, and if we didn't know what any initial values, then we would not be able to find the c. We wouldn't be able to determine that constant. But as you saw in the last problem, we were able to determine a specific value for c because we were given an initial value. And so I didn't draw these graphs very carefully, but so one of these may or may not be the one that goes through. It should go through negative 1, 0. But if we did plot the point negative 1, 0, then we would see that point right there. Okay, so this is the point, and we know that. We know that negative 1, 0 are the coordinates of that point right there. And there is a graph, an antiderivative of 2x that actually goes through that point. And if you're really following along well, you would see that this is actually the one that goes through like that. And the equation for this function would be x squared minus 1. Y equals x squared minus 1. So that's one way you could do it. It's rarely that easy to do, and you may have that might not have kind of been translated to you real well. But we'll go through the problem like this. But graphically, that is the solution. And again, let's do that algebraically, or using what we know to be true. And we are now down to algebra because we're given. In fact, you've done these in algebra. You're given x, you're given y. So the ordered pair, negative 1, 0, satisfies this equation because it's a point on the curve. So way back when, and I do this with my algebra students, why does the curve look like that? Well, the curve looks like that because it's a collection of points whose coordinates make this equation true. I would replay that if I were you. A graph of a function is just the collection of points whose coordinates, the x and y coordinates, make this equation true. I would love for you to be able to say that. It would be music to my ears if you could say those words to me. You come into class tomorrow and say, hey, Mr. Hawks, a graph is just a collection of points whose coordinates, x and y, satisfy the given equation. It would be awesome if you could say that. So anyway, if negative 1, 0 satisfies this equation here, then we know that we could replace 0 or y with 0, and we could replace x with the number negative 1, and we'd get 0 equals 1 plus c. In other words, subtracting 1 from both sides, we would get that c is equal to negative 1. And just like I said, guys, that the equation of the solution, so the solution to the initial value problem is right there. Okay, so that's the solution to the initial value problem. Any questions? Okay, good. So then number 5, 5, 6, and I would challenge you to do number 7 on your own as well. Number 6, you have to take it all the way to the second derivative, so maybe you'll watch me do number 6 and then you'll try to do number 7 as well. But please pause the video, please try number 5 on your own, and then we will just play the video when you're ready. Okay. We know that the family of antiderivatives, family of solutions, the general solution, or I guess you could say, would be y equals the derivative of the sine is the cosine. So antiderivative of the cosine is sine, and an antiderivative of the sine is negative cosine. Okay, but don't forget the plus c. Okay, and again, here's our x, here's our y. So we replace y with 1. We replace x with the pi. Okay, this is where students always get messed up here. You try to skip steps, and why you would do that, I don't know. Sine of pi is 0. Cosine of pi is negative 1. So we see we have minus minus. Okay, and minus minus means plus plus. So we have 1 equals 1 plus c. Well, guess what? When we subtract 1 from both sides, we get that c has a value of 0. And if c has a value of 0, then the solution to the initial value problem would be y equals that antiderivative that we got up there plus 0, and so we just don't write plus 0, we just leave it alone, and that is the solution to the initial value problem. And that's good. Good job. I'm saying good job because I'm assuming you got it right, and if you didn't get it right, then maybe watch me do number 6. If you did get that one right, I challenge you to try number 6 on your own. It's just the initial value problem twice. Okay, so keeping in mind, and I think this would be maybe a good thing to do, to remind you that y, not y equals, sorry, y, and then we have dy dx. Remember when we go to the right, we're taking successive derivatives? Okay. So all you have to do in this type of problem, when you're given the second derivative, then you just go back and find the first derivative, given the first derivative's initial value. And then once you find that specific function, the solution to that differential equation, then you're going to find the y, the solution to the other initial value problem. Okay? So that's the idea behind this problem. And maybe if you didn't know what to do, maybe you try it now. Okay, but let me erase some of this stuff here, and then let's get started. So we start with this function here. The antiderivative, that would be dy dx, then would be 2x minus 6x squared over 2, which would be minus 3x squared. Okay, again, we can't forget about that plus c. And so we know that y prime at 0 is 4. Okay, so again, guys, this is the x, this is the y, or in other words, y prime. Okay, so if that's the y prime and this is y prime here, dy dx is the same as y prime. Okay, and that's 4 when x is equal to 0. So we have 0 minus 0 plus c, so c is 4. And so therefore we get, what should we do that in purple? We would get dy dx is equal to, what did we say, 2x minus 3x squared plus 4. Okay, we're going to need a little bit more room down here, so let me white out some of that stuff. Okay, and now we have our new differential equation, of which we now need to find an antiderivative. So y is equal to 2x squared over 2 is x squared minus 3x cubed over 3 would be x cubed. Okay, plus 4x, and then again plus c. Well, let's look back at our initial condition. Our initial condition is that y of 0, that would be the x, is equal to 1. That's our y. Okay. Well, what did I say? 1? Y is 1? Yeah. So we replace y with 1. We replace x with 0. So you can see this term goes to 0, this term goes to 0, this term goes to 0, and all we're left with is c. So therefore, we have y equals x squared minus x cubed plus 4x plus 1. And that, ladies and gentlemen, is how you solve an initial value problem where you're given two initial conditions because you were given initially the derivative, the second derivative of y with respect to x. Okay, last problem, and I encourage you to now try number 7 on your own. And we're given the acceleration, and we know then, I like these better because it actually puts more meaning to what we're doing. We know that the velocity is the antiderivative of the acceleration, and so that would be sine of t plus c. Antiderivative of cosine is sine. And we know that velocity at 0, so when we put a 0 in for x, velocity at 0, or for t, is equal to the sine of 0 plus c, which is equal to negative 1. We know that the sine of 0 is 0, so we get that c is negative 1. So we go back to this, v of t, and that's equal to the sine of t, again, plus c. Well, we again determined that the c was negative 1, so we just replace c with negative 1. Okay? And then the v of t, antiderivative of v of t, is s of t. Okay? At least that's what it was given to be here. So s of t given to be the position. The antiderivative of the sine is negative cosine t. Okay, be careful here because the antiderivative of a constant is just the constant itself. Sorry, not the constant itself, the variable itself. So the derivative of t is 1, antiderivative of 1 is t. Okay, and don't forget the plus c because we have to add in our initial condition. So we know that s of 0 is 1, so we write s of 0 is equal to negative cosine 0. This is where students make so many mistakes. Whenever you deal with trig, and that has a value of 1, right? Did I get that right? S of 0 is 1, yeah. Guys, be really careful when you're dealing with the unit circle because you can do all the calculus right and then totally mess up on the unit circle values, and it's very, very frustrating for you because you know how to do this, the calculus part of the problem, and then you mess up on the trig. So anyway, that's why those the red quizzes are what I feel very valuable. Anyway, cosine of 0 is 1. Okay, so many students put 0 there, and we end up getting negative 1 minus 0 plus c equals 1. I've even seen students get all the way to here and say that c is equal to 0. I mean, come on, you know how to do that. C is equal to 2. And so if c is equal to 2, we say therefore, let's put this right over here, therefore our s of t, where's our initial s of t, is equal to, I didn't leave myself a lot of room, did I? Well, let's just put it right here, equal to negative cosine t, and then we had the minus t, and then what was c equal to? C was equal to 2. And so there we go. That, let me put a box around the whole thing. Therefore, s of t is equal to negative cosine t minus t plus 2. And that, ladies and gentlemen, again, is the solution to the initial value problem, given the two initial values of both the position and the velocity at time 0. One thing to keep in mind is that we get to, you may not be aware of this or not, but we actually are going to use this kind of stuff. It's important that we understand why we're given an initial condition and then and we're asked to evaluate the function based on a rate of change. Okay, so we can tell a lot about things just by knowing having a known value and its rate of change. So like positions of planets can be determined, future positions of planets can be determined from present positions, and then the velocity at a certain time, a certain position, the velocity at a certain position, then you can anticipate where the planets are going to go. So there's lots of other examples which you'll see, but I want you to know that this is a very important part of calculus, which it seems like every time we get to a new part, it's also a very important part. So I guess as a general rule, it's all important, but these kinds of problems come up a lot. So anyway, we'll see you in class, and I may or may not post any new problems on Canvas before you come in tomorrow, but check the Canvas site, and I'll see you tomorrow.